Good evening, everyone. Welcome to the NPTEL course, Control and Tuning Methods in Switched Mode Power Converters. So these sessions are the problem solving sessions where I'll be solving the problems, clearing your doubts, as well as clarifying uh, any doubts you have in the theory. If needed, I will also teach part of the theory. So let me share my screen and give an introduction about myself as well as this course. Let me know once you can see my screen. Can you see my screen?
Yes, sir.
Okay. So as you know, this is a control and tuning methods course for switch mode power converter. So here extensively, Professor Santanu Kapat will be teaching about the control methods as well as how to tune regarding modeling as well as the MATLAB simulation. So today's session will be week one, which will be switch mode power converters and MATLAB simulation. And just to give a brief introduction about myself, I am Teja Golla. I am a PhD scholar working under Professor Santanu Kapat, and he's also the course instructor for this particular course. So currently I'm pursuing my PhD under him, and I am conducting this live problem solving sessions as a part of my PMRF scholarship. So previously I have conducted such problem solving sessions for various courses, and all of those details you can find in my website. I'll also share the details of these links which will be needed for you throughout this 12-week session. And one more thing, since this course is 12 weeks, I'll be conducting 12 such 1 hour problem solving sessions. And it's supposed to happen every Monday from 6 p.m. to 7 p.m. In case if I'm out of station or if I'm unavailable, then either it will be preponed or postponed, and that will be informed through your email. Like where you are getting these notifications for this live problem solving sessions. So I have completed my BTech under Professor Santanu Kapat, and I have converted to PhD, and I'm currently working on that. So just to give a course outline for this course, so it has 12 weeks, and week one, which is today's session about, is switched mode power converters and MATLAB simulation. And week two will be about modulation techniques in switched mode power converters. And week three is about fixed frequency control methods. And week four is about variable frequency control methods. And week five is about modeling and analysis techniques in switched mode power converters. And week six is small signal performance analysis. And week seven is small signal design and tuning of PWM voltage mode control, followed by small signal design of current mode control, then large signal model and why it is needed, as well as nonlinear control. Then week 10 is about boundary control for time optimal recovery, and week 11 is large signal controller tuning method, and week 12 will be performance comparison and simulation. So in this course, you will be extensively learning about starting with modeling of a converter, then how to design it, power stage design, then how to implement it in MATLAB using Simulink blocks, then running it in open loop, then how to get the model for closed loop, whether it be voltage mode control or current mode control, how to design the controller, and then implement it in the MATLAB, and then checking its performance. So this is under small signal design. Then we'll move to large signal design. For that, we'll need large signal model. So we'll answer all these questions about why we should do that, and how we should do that, and when we should do that. So when we are designing something, say small signal design, why will we do small signal design, and how to do small signal design, and when can we do small signal design. Same with large signal design or boundary control. So these questions will be answered in the or have already been answered by Professor Kapat in his lectures. So just to give clarity about this problem solving session, so many people have misconception about these problem solving sessions. So this is not at all a replacement for the lectures that sir has taught in all the weeks. Say 6 lectures are there in week one, probably in all the weeks. So around say 5 to 6 lectures are there in each week. So this problem solving session is not at all a replacement for those lectures. In fact, you should go through those lectures and then attend these sessions, because here I'll be solving the problems directly. And then if you have any queries about any concepts, or if you are not clear about any concept, if you are facing struggle in understanding any concept, then I'll explain that. But if you expect me to teach whatever sir has taught in this 1 hour, then it will be difficult. So last year I have conducted 2 hour session, but since my TA requirement is 1 hour this semester, I'll be conducting 1 hour session instead of 2 hours for this entire semester, which is 12 weeks. So I'll be taking 1 hour sessions every Monday. And in my previous year, the plan was to take 2 hours. So I used to summarize the concepts in the first 1 hour and then solve the problems and clear the doubts if the students had any in the second hour. But now since we have only 1 hour, I don't want to waste the time re-explaining what sir has told. So I will be mainly concentrating on solving the problems instead. But if you have any query in the concept, I'll be teaching. But don't consider that I'll be teaching or summarizing again what sir has already taught. So this session main objective is to solve the problem so that you will be habituated and you will be more comfortable solving the assignment. So I'll try to solve few problems that will help you with the problems in the assignment. Yeah, so whatever I have summarized, first, if needed, I'll revise any relevant theory, that too maybe in 10 to 15 minutes if needed, because the session is for 1 hour. Then I'll solve few examples which will be helpful for you to understand the concepts, as well as it will help you to solve the assignment. So I'll take similar problems, not the exact problems, of course. And then if you have any doubts or any difficulty in understanding any concepts, you can ask me in this session, and I'll try to clarify those doubts as well. So this is my channel. I'll again share the links in the comment section as well. So whatever sessions that I'll be conducting, in this case 6 p.m. to 7 p.m. every Monday, I'll be recording these sessions, and these are being recorded, and I'll upload it to my YouTube channel so that you can go through those videos at any time after the session as well. And the lecture notes, whatever notes that I have considered, or whatever notes or problems I'll be solving, that I'll be uploading to the Google Drive, where you can find. So this link will be mentioned in my YouTube channel, YouTube video description as well. So keep these links ready with you. Let me share it in the screen. So someone is saying kindly share the screen, but I have shared the screen. Can anyone please confirm whether you are able to see my screen or not?
Yes, sir. We are able to see your screen.
Okay, okay. So maybe, sir, you might rejoin and check if you are able to see my screen. Yeah. So let me share the links that I have mentioned here. So these links are critical. So let me quickly share it. Yeah. So I'm sharing list of links starting with my website, where under the YouTube section you can find details regarding this playlist. And second one is my YouTube channel, where I'll be uploading all the recorded sessions. And the third one is link to the Zoom meeting. So the link will remains the same over the entire semester. So every week we'll come back here and then have the discussion in the same meeting. So please save this somewhere. And then I have done this course last year as well. And as I have mentioned, last year I have conducted 2 hour sessions. That was my TA requirement. And this year I'm conducting 1 hour. So if you want to go through a shorted summary version of what sir has taught, you can go through my previous year YouTube playlist in the first 1 hour. So where I have basically summarized. So again, it is not a replacement for watching the lectures. You must watch the lectures before attending this session, so that this will be helpful. If you come here without going through the lectures, then you will not understand anything, because we are directly solving the problems. And the last one is the Google Drive to access these notes. So whatever PPT or whatever notes, whatever problems that I will be solving, all the notes will be uploaded to this Google Drive week by week basis. So I'll create subfolders from week 1 to week 12, and I'll upload all the materials that I will show in these sessions to this Google Drive. And coming to one more thing. Yeah. So whatever notes or problems that I have solved. So this notes is from my previous year. So last year also this course was running, and this year also it is rerunning again. So this is the notes or the concepts that I have taught in my previous video. So due to this reason, I don't want to teach it again because it is already available online. Instead, I would like to spend this time more effectively by solving the problems, which I believe would be more useful for you rather than teaching the concepts again, which are already available in Sir's lectures as well as my previous year playlist. So last year I have spent more time on explaining. This year I'll try to reduce and spend more time on problem solving instead. So can you please confirm whether you are able to access all the links that I have shared? Can anyone confirm if all of them are working?
Yes, sir. Yes, sir. We are able to.
Okay, okay. So now, yeah, if you have any queries till now, you can ask, else we can start with this uh, session, today's session. Any queries?
Yes, we can start with the sessions.
Okay, okay, yeah. So this week is more of switched mode power converters. So sir has explained various converters like buck converter, boost converter, as well as buck boost converter, their input output voltage relationship, how to design it. So I'll just draw the circuits of buck as well as boost as well as buck boost so that it will be just like a quick summary. So starting with the buck converter. I hope you are able to see me writing. So if you face any issues at any point of time, please feel free to stop me and then we can have discussion on that. So this I'm representing as a switch. So this is capacitor. This is resistor. I say this is Q, this is Q bar. So why these switches are always complementary? What happens if I close both the switches? Anyone?
The supply will be shorted.
Yes, yes. So if I close turn on both the switches, then supply is basically shorted. So we are short circuiting the supply. So that's why it is very critical to not turn on both. So for switching this, what we do in practical situations, it is called break and make mechanism, which means first we'll break the path. So we'll say if Q is on and Q bar is off, first we'll try to turn off Q also. So both the switches will be off, then I'll turn on Q bar so that I'll not make a mistake of turning on both the switches at a time. So when both the switches are off, there is no path for the inductor current, right? In such case, it will pass through the diode, which is by default there in the MOSFETs. So when both the switches are off, then the current will flow through the diode because I cannot, the inductor current cannot be discontinuous, right? I cannot close the path. If there is any step in the inductor current, then what will be the voltage? So VL is L di by dt, right? So if there is any step change in the inductor current, then there will be impulse because the derivative of step function is impulse. So if there is any step function or a step change in the inductor current, then there will be a voltage spike. So the spike is impulse, so it can be anything. So that's why we always have to make sure that there is a path for the inductor current. We should not break the path, else there will be spike and then the components will get damaged. So can anyone tell me the input output relationship for a buck converter?
V naught equal to dV.
Yes. So for a buck converter, V naught is equals to dV in. And the range of duty ratio?
0 to 100.
0 to 1.
Yes. So
0 to 1.
duty is a ratio. So duty ratio is from 0 to 1. Sorry. So is buck converter a step up or a step down converter?
Step
Step
down.
down.
Step down. Because the output voltage is always lesser than this. So it's a step down converter.
So voltage will be bucking and current will be boosting, right?
Yes. Current Yes, yes, exactly. So output current will be more than the input current, of course, because sorry.
To match the input power equal to output power,
Yes,
right?
yes, very, very good. So if you match the input power and output power, so P in is equals to P out. So assuming 100% efficient, which is this not, so idealistic case, V naught into I naught. So if you consider average IN, it will be I naught by D by substituting the V naught expression. So with this, we can say that the input current is lesser than the output current. So the power remains the same. So if we are increasing the voltage, current has to be gone down, of course. So now I'll not tell the converter, I'll draw the circuit. You let me know which converter is this. Can anyone tell me which converter is this?
Boost
Boost
converter.
Yes, boost
synchronous.
converter. Yeah, synchronous. So if we are using diode instead of a switch, then it is asynchronous because diode will not let the current go below zero. So that's why it is called asynchronous. If we are using switches, then it is synchronous. Current can go negative, but there will be a diode parallel to the MOSFET that comes with the MOSFET. That is because of the physics of the MOSFET. We are not separately adding a MOSFET, but the MOSFET inherently has a diode. So can you
So,
tell me?
so
Yeah,
please,
yeah.
can you classify that synchronous that I couldn't get in?
Okay, okay.
If you are
So
using diode, it is good.
yeah, yeah. So okay, let me do one thing. Let me create some space here. So I'll explain for buck because it will be simpler there. So if I have a switch, one is switch, another is diode. Okay, so say this is Q, and then now diode is there. So there is no signal for diode. This is V in L, C, R. So now if you see, the current is always flowing in this direction, right? So for the input, it is okay. But the current that is flowing through this cannot go negative because diode will conduct only in one direction. So in this case, current will not go negative. So instead, it will be cut down at zero. So it will be zero, something like this. So this configuration is called asynchronous because of the diode. Whereas if we have diode, if we have switch, then current can go negative. So it can go below zero because the switch can conduct in both the direction, whereas the diode cannot conduct. So this switching configuration network is called synchronous.
Okay, sir. Okay, sir.
Okay.
Thank you.
Yeah. 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 So for boost converter, can anyone let me know the input output relation?
Not
V not
equal to
equal to
V in by 1 minus D.
Yeah.
yes.
So V naught is equals to V in by 1 minus D. So is this step up or step down?
Step up.
Step up, yes. Yeah. So one more converter is there. So let us quickly discuss this before we start solving the problems. So can anyone identify this converter?
Buck boost.
Buck boost, yeah, very good. Input output relation.
V naught by V in equal to D by 1 minus D.
Are you sure, or anything you're missing?
V naught equal to alpha by d Vs by 1 minus d.
Okay.
That's what. Equal by
Yeah,
V.
but are
It's a
you sure?
combination of buck and boost, right?
Yes, yes. But whether V naught will be positive or negative?
Negative.
Yeah. So
It
you are.
depends on duty
Minus D
ratio.
by 1 minus D. Correct.
Yeah, yeah. So based on the configuration that I have given, the plus minus that I have mentioned at the output, it will be minus, or I have to interchange the minus and plus. So if I'm considering the top terminal as positive, then V naught is basically minus D by 1 minus D. So
Yes.
this
Yes.
is, yeah, V naught is equals to minus D by 1 minus D into V in. So this is, it can step up as well as step down. So it can do both,
Yes.
step up as well as step down. So this is, these are the basic converters that were discussed by sir in the first week. I just wanted to show the converters as well as the conversion. But how
Yes.
are we going to design this? So I have couple of problems where I have given some values, and then we'll also see how to design this. So this is what I wanted to summarize the concepts. But as we move more into upcoming weeks, then there will be more technical, because this is week one. It was more of introductory, so not much of the concept. But as we move further, I was also planning to show you MATLAB, and I recommend you to make the MATLAB simulation, because from my experience, when I've started making MATLAB simulation, at the beginning things may not work because we make mistakes. But when you start debugging and finding out where those mistakes are, and then when you try to rectify them, that was the process where you will learn. Because if you directly make the converter and if it runs, you are not getting or not understanding in detail where things can go wrong, or where or how the things are working. But say if things are not working, then you have to understand each and every block, how it is supposed to work, and then whether it is not working accordingly or not. So then you will try to go deeper, and then you'll get a better understanding. So I always recommend you to make your own MATLAB simulation. And sir has also showed, so you can start making the simulation by looking at the videos, and eventually you'll get the confidence and you can make the models by yourself. So
Okay.
if you have, yes, if you have any queries so far, you can ask, else we'll start solving.
No, nothing. We can proceed.
Okay. So I'll read out the question. You may start solving also. So consider the given circuit. It's a basically resistive divider. So what will be the output voltage, and what will be the current flowing through the 1 ohm resistor, and what will be the theoretical efficiency, output by input.
The current is 1 amps.
Yeah.
Output voltage is 4 volt.
Yes. Very good.
And efficiency will be 4 by 5. So around 80 percentage.
80%. Okay. Good. Let us check. What about others? Are you trying to solve? If you have solved, you can let me know the answer, or you can mention in the chat box also. Yeah, since this is an easy question, I hope you will be able to do. So let me quickly solve it. So first we can calculate the current, which is 5 volts by 1 ohm plus 4 ohm. So this will give me current as 1 ampere. So if I got the current, then I can solve for the V naught, which will be 4 ohm times 1 ampere, which means V naught is 4 volts. Now, if we are talking about efficiency, which will be P out by P in. So power I can write as voltage into current, and since the current is same, it will be the ratio of the voltages. So output voltage we are getting as 4 volt, input is given by as 5. So efficiency will be 80%. Yeah. So I hope everyone is able to solve this.
Yes, yes,
Okay. So can we move to next question?
yes.
Okay. Yeah. So the next question is based on buck converter. Let me read out the question. Consider a buck converter with the following specifications. V in is varying from 8 volt to 12 volt. V output is V out is regulated at 1 volt. Switching frequency is 1 megahertz and load current is 20 amperes. So design a inductor such that the worst case inductor current ripple is less than 30% of its average value. Can I say now there are subsequent questions. Can I select an inductor with an inductance of 180 nanohenry? If yes, please justify. Same I have asked for 120 nanohenry. So subsequently there are few more questions. What is the drawback of selecting an inductor that whose value is smaller than the required value, and vice versa? If it is larger than the required value, what will be the drawback or what will be the consequence of that? So anyone how to start or proceed with this question?
Actually, the value of the inductor determines whether the converter will be operating in continuous conduction mode or discontinuous conduction.
Yeah, that is one thing. Say the converter is synchronous, so it can operate in continuous conduction mode.
Okay.
Okay, just
So
think about
based
it.
on
In the
the
meantime,
design
I'll draw this
equations,
circuit. Yeah, yeah.
based on the design equations, we'll be finding the value of minimum value for critical
Yes.
inductance value.
For the from the continuous conduction mode or like which design equation?
From continuous, assuming it is operating under continuous conduction.
Okay, okay. So that is one way of thinking, but I have given one condition, right? The inductor current ripple is should be less than 30% of its average value. So from there, can we calculate any inductance or?
LI,
Based
LI
on the
value.
current ripple formula, we can decide. F we know, del IL we know.
Yes.
From that,
Okay.
we can
So
decide the duty cycle.
yeah, very good. So let me write, or can you tell me the equation before I write? Anyone for current ripple?
LI equal to dV in by del I into Fs.
Okay, just a minute. I'll write first VL equals to L into DIL by dt. Huh? Now tell me
Uh,
delta
LI
IL is equal.
equal to
Yes.
del IL equal to
Uh-huh.
dV in by
dV in by
del I into, sorry,
L.
Fs into L.
Yes, yes. So, but it is not dV in, right? It should be D into V in minus V0, right?
D into V
V in
minus
minus
V0.
V0. Yeah. So let me write it for simplification. So VL is when the switch is on, VL is V in minus V0, and when the switch is off, it is minus V0. And this is during DTS time, and this is during 1 minus DTS time. So we can consider any region, and the result is the same at steady state. So if I consider the first one, then delta IL is V in minus V0 into V0, sorry, into D into time period T, or I can write in switching frequency by L. So now what I would do is I will convert everything in terms of V in and V0 because the data that is given is V in and V0. I don't want to be in terms of duty ratio. Why? I'll let you know once I solve this. So what is duty ratio? It is V naught by V in, right? So say switching frequency is given, so I'll write it as L into FSW. So now I'll further simplify this as V naught into 1 minus V0 by V in by L into FSW. So this is the equation that I am getting for designing the inductor. So keep one thing in mind. We don't design the inductor based on the continuous conduction mode. So we design the inductor based on the ripple. So what will be decided for continuous conduction mode? That load decides. So the resistance R will decide what will be boundary conduction mode, continuous conduction mode, as well as critical conduction mode. So inductance is designed based on ripple, and the load R will be decided based on the critical conduction mode. And also R is user defined. So we are making a power supply and we are giving to the consumer. So the load will be decided by the application. But if you want to see where it starts continuous conduction mode or discontinuous conduction mode, then we have to calculate the R accordingly. Okay, so now coming back to this question, I have obtained the expression. I have V naught, I have L, I have switching frequency, I have V in. But I have given a range of V in. So which V in should we choose? Anyone?
8 volt.
Okay, and why? Any reason?
Just like that I'm saying I am not having any.
Okay, okay. I mean, I just wanted to try. You may be wrong, but I'll explain the logic. So in that way only you learn. Okay, so whenever we are designing inductor or capacitor, we have to design based on the worst case situation. So here I have to design such that the worst case inductor ripple is 30% of its average value. So let us first calculate the value. So what is 30% of 20? 6 amperes, right?
Yes.
Yeah. So it means my delta IL maximum should be less than 6 amperes at all costs. So no matter the input voltage, it should always be less than 6 amperes. So now this will raise a question: when will it be worst case? Like when will be the ripple at its maximum value? Since V naught is regulated and V in is varying, now we have to ask ourselves the question: at what input voltage is the inductor current ripple maximum? So from this expression, let us say V in is minimum, then V naught by V in will be maximum. 1 minus V naught by V in will be minimum. So at minimum voltage, we are getting minimum ripple. So now if you consider V in to be maximum, V0 by V in will be minimum. 1 minus V0 by V in will be maximum. Since there is one minus sign and one inverse sign, so it is basically proportional to V in. So at maximum input voltage, we will get the worst case ripple for a buck converter. So we have to ensure that we have inductance such that even at an input voltage of whatever is the maximum value, here it is 12 volt, the inductor current will be less than 6 amperes. So at a lesser input voltage, say 8 volt, it will anyways be lesser than 6 amperes because there it will be the minimum value. Is that clear? Does that make sense?
Yeah. Understood.
Yeah.
Clearly understood.
So now if you calculate, so I hope you have calculators. Please calculate. So V naught I have given 1. Another V naught is also 1 because it is regulated. Input is 12. And then I have to calculate the inductor, and switching frequency is 1 megahertz. So 10 to the power minus 6. This should be less than 6. So now I will take the inductance on the other side. So inductance is greater than 11 by 12 into 6 micro. So please calculate and let me know the value. And what is the minimum inductance that we should design? So L should be greater than what? Let me know in nanohenry. It will come in nanohenry.
Sorry, not having calculator. It's in college.
Okay, okay. So what about others? Do you have calculators? Or let me calculate.
So doing, sir.
Okay, okay. Yeah, please do. Let me know in nanohenry.
152 millihenry,
Milli or nano?
sir. We should clear them. Sorry.
Are you calculating? Okay, I have calculated. Anyone with the answer? If you have mobile, you can use your mobile. No one?
0.152 into 10 power 6.
Yeah, right. Very good. So 0.152 microhenry, if I convert to nanohenry, it will be 152.7 nanohenry. So the minimum inductance required to keep the maximum inductor current ripple below its 30% is 152 nanohenry. Okay. So now let us go back to the other question. So can I select an inductor of 180 nanohenry? My
So
minimum value
180.
is 152 nanohenry. So can I choose 180 nanohenry?
Yes, yes, you can
Yes.
use.
Yes, we can choose 180 to 180 nanohenry. Can we choose 120 nanohenry?
No.
No, because
No.
in or for some certain input voltage, my inductor current ripple will not be less than 30%. It will exceed 6 amperes. So we cannot use 120 nanohenry. So now another question is, since my inductance is minimum inductance is 153 nanohenry, say rounded off to 153, I can use 180 nanohenry. I can use 220 nanohenry. I can use 1 microhenry. So what happens if I choose a value larger, and what happens if I choose a value smaller? What is its impact? Anyone?
If you choose smaller value, discontinuous conduction mode may occur.
Okay. Actually, the continuous conduction mode is dependent on the switch configuration. If we are not using diode, it is always CCM.
Okay.
Okay. And one more thing,
If
I
you
don't
are
have, just sorry for interrupting. I don't have Zoom premium version. So the meeting will end after every 40 minutes. So the meeting might end in a minute. If it ends, please use the link and join back, and I'll also join back. So please bear with this. Every week this happens. After 40 minutes, meeting will automatically end and will be thrown out. We have to join back. Yeah, sorry. Please
so
continue.
if we choose less inductance, the current ripple may be
Yes, very
more.
good. Yeah, very good.
Current
That's
ripple will
the
be
correct
more.
answer. Ripple will be more. And what if we choose larger, much larger value?
Less ripples, less current ripple.
No
Yes, but
drawback
is
there.
it okay? Drawback. Like I am fine with the lesser current ripple, but what is wrong choosing much higher value? So coming back to the question, say ripple will be high, which is not desired according to our requirement. So there is some issue. What happens if I
This
choose much
inductance
larger?
is this converter will be bulky.
Yes, very good. Converter will be bulky. So that is one thing, we don't want bulky converter because it will increase the volume, also the weight. So bulky, when we mean bulky, it includes both weight and volume, weight plus volume. And the other one is transient response will be poor. Poor transient response. I'll come to this. Why poor? Because say uh, our inductor current in a buck converter, the slope, this one is V in minus V0 by L. So it is inversely proportional to L. Smaller the value, higher is the slope. Higher the value, smaller is the slope. Say if I have a load transient, then I can go say this is an optimal condition. Say I'm going from one load condition to another load condition. Now if my slope is lesser, then I'll take more time to reach the same load condition. So my transient response is taking more time. So I don't want to go much higher value than required, because that will increase the weight as well as volume of my converter, as well as it will degrade the transient response. So that's why I'll choose the nearest available inductor. Say 152 is the nanohenry, I'll see 160 is available or 180 is available. So I'll go with 180. I could go for 220 or 330 nanohenry or 1 microhenry, but that will increase the size as well as degrade the transient response. So I would like to choose the nearest value above the required value. So 152 means I'll go with 160 or 180. Is that clear?
Yes, sir.
Hello. Okay. So coming to the next question. So the pace is okay, right? I'm not going too fast or too slow, right?
Yeah, fine.
Okay. So consider a boost converter operating at fixed frequency with the following specifications. Input voltage is given, output voltage is given. Find the range of the duty ratio and find the input voltage at which the inductor ripple is maximum. So second question is kind of similar to the first question, because we also have to know when the inductor current ripple is maximum, because at that condition we have to design the inductor so that at every other condition ripple will be smaller than this value. So for a boost converter, V naught
One
is,
second, let me clarify one thing.
yeah.
Sorry for it.
No, it's okay.
See, so whenever we are designing the inductor, we should choose for while designing, we have to choose a maximum input voltage, right? Last time we have discussed like.
That's a buck converter. So I have to
Okay,
choose.
depending upon the value of equation.
Yes.
How it is going to play.
Yes. So I have to choose that condition where the ripple is maximum. So in the buck converter, it happens to be at maximum input voltage, or I would say lowest duty ratio, because I have to see when delta IL will be maximum. I have seen that when V in is maximum, delta IL is maximum. So at highest input voltage, if I could limit the current ripple, then for all the cases, I could still limit it. So that's the plan.
Depending upon the location of V in, we have to choose it.
Yes. So in the case of buck converter, we have realized that at maximum input voltage, it is worst. So I have given another such example for boost, so we can compare where it is worst. So it will not be, of course, at maximum input voltage, but we'll see where it happens.
Okay.
So for boost
here
converter,
V naught by V in is 1 by 1 minus D.
yeah. So V naught is V in by 1 minus D. So if I calculate duty ratio, 1 minus D is basically V in by V0, and then duty ratio is nothing but 1 minus V in by V naught. So I need minimum and maximum duty ratio, which will happen at minimum and maximum input voltage. So can anyone tell me, quickly calculate duty ratio and let me know the range, D minimum and D maximum? D minimum as well as D maximum. And I also suggest you to do as many calculations as possible, because then you will be more comfortable with math. If you ask me, I'm more habituated to calculator as well as calculating in mobile phone. Now I am very prone to make mathematical mistake. But if I have to give an exam, I should start doing the calculations by myself and practice more, so that I'll make less mistakes in the exam. But since anyway calculator is there.
0.2 to 0.8, sir.
Yes. So D minimum will be 1 minus 4 by 20. So it is 1 by 5, 0.2. And D maximum?
0.8.
0.8. Yeah, very good. So I hope everyone is able to do. If you have any queries, please feel free to ask. Don't think that others are able to do and you are not able to do. If you have any query, even if it's a small, please ask. No question is silly question. Every question is question. I don't consider anything to be silly. Okay, so now for boost converter, let us see at what condition ripple is worst. So for boost converter, if I draw the circuit, this is switch. Okay, so VL is equal to LDIL by dt. Say I consider during dt. So during dt, voltage across inductor is V in. So V in into D by L into Fs is nothing but delta IL. Is this clear?
Yes.
Yeah. So now what I would do is, in the previous case, I have written everything in terms of V in and V naught, but in this case, I would do slightly different. So what I would do instead is, I'll convert V in terms of V naught and 1 minus D. So V naught and 1 minus D. V in is V naught into 1 minus D. Now that I'll substitute here. You'll know why once I get the expression. So now it is V naught into D into 1 minus D by L into Fs. V naught is fixed. L is what we are calculating. Fs is fixed. So delta EL will be worst when D into 1 minus D is maximum. Agree?
Yes.
So when will this be maximum?
For minimum value of, sorry, for
It is quadratic, so we can't directly say. You can differentiate it with respect to D to get that. Say if I consider this as a function of D, D minus D square. So dou F by dou D, if I equate it to 0, then I'll get 1 minus 2D is equals to 0. So at duty ratio of 0.5, D into 1 minus D is
Sir,
maximum.
can you repeat this
Yeah,
again,
yeah.
please?
Yes, yes, yeah.
After the second equation, del IL equal to V naught into D 1 minus D. After that, can you please?
Okay, okay. So
Yes,
I have substituted my V in value in terms of
yes, sir.
V naught and 1 minus D, because I want
Yes.
everything to be in D for this case, because it will
Okay.
make my understanding simpler. So that's why I have converted everything in terms
Okay.
of D. Now V naught is fixed, L is what
D.
we are calculating, which is also again is fixed. Switching frequency is fixed. So now delta
Fixed.
EL will be maximum when D into 1 minus D is maximum. So now I
Maximum.
am
okay, okay.
calculating when this is maximum. So if I do not know what I would do, I would differentiate it and see at what value it is becoming 0. So the derivative is 0 means either it is minimum or maximum, but in this case it will be maximum. This I can also get it by drawing the plot, but I'm not going into those details because that is known. So at D equals to zero point 0.5, this will be maximum. Whereas in the case of buck converter, it is maximum at maximum V in. So as you see, based on the converter, the worst case is changing. So if anyone asks me design a boost converter so that the ripple doesn't cross this, I will try to see at D equals to 0.5. So now for the second question, they are asking what is the input voltage at which the inductor current ripple is maximum. So now tell me at what input voltage. So duty ratio is 0.5. So now calculate and tell me what will be the input voltage. So for duty ratio to be 0.5 and output voltage to be 20 volt, what will be the input voltage? Can you use this equation V in equal to V naught into 1 minus D? V naught is 20 volt. So for duty ratio to be 0.5 and V naught is 20 volt, I can calculate my input voltage as V naught into 1 minus D, which means 10 volt, right? Hello?
Okay, sir.
Yeah. So in this, had this been buck converter, my input at 16 volt of input, my ripple will be maximum. But since it is a boost converter, at input voltage of 10 volt, which is 2 times that of output voltage, it is maximum. So I have to see for which converter I am doing and what exactly I am doing. So these are some results that you can remember, that for buck converter at maximum input voltage current ripple is maximum, and for boost converter it is at D equal to 0.5. But I just wanted to show you by solving, so I have considered these two problems.
So for a boost converter, whenever the duty ratio is 0.5, we'll be having a maximum.
Yes, yes, yes. And now
So
another, yeah, please tell me.
irrespective of the input voltage.
Yes, yes. So now again, here the input voltage range is in such a way, chosen such a way that D is equals to 0.5 is falling in that range. Say if it is not falling in that range, then you have to see at what duty ratio we can go up to, and then you have to check at that condition. Because if I choose V in to be 12 volt to 16 volt, in that case, D equal to 0.5 is not possible. So then there will be slightly different. These problems, more complicated problems, will be solving in the upcoming weeks. So don't worry. In this week it is simple things. So we'll start with simple design.
Okay, fine.
Any queries? Okay, so if no queries, then let us solve another problem on buck boost converter where input voltage is 10 volt and V naught is minus 15 volt. So the first question is find the duty ratio, and the subsequent questions are what will be the range of duty ratio such that mod V naught is less than V in, and what will be the range of duty ratio such that mod V naught is greater than V in. So I'm considering magnitude and not the absolute value.
Sorry,
Yeah, so in the first
can we
problem,
one second?
yeah, I'll repeat.
One second.
So
Can we go to the third question? 1 second.
okay, yeah, sorry, yeah.
See, first question they have asked us find the range of duty ratio, but that we have found out.
Yes,
Find the input voltage at which the inductor current ripple is maximum.
maximum.
So first, we have found out the condition at
Yes,
when the inductor current ripple will be maximum.
yes,
Then we have substituted that and we have found out the input voltage.
yes, you're right.
Fine. Thank you, sir. Thank you for that. We can
Yeah.
go to the fourth question.
Okay, yeah. So in this problem, I have given buck boost converter. So first solve for the duty ratio and then solve for the range of duty ratio for these conditions. So once you solve B, you can get C. But I just wanted to discuss regarding that. So I have given both the sub problems. So as you know, V naught is minus D by 1 minus D. So I'm muting. I think there is some noise. Let me mute. Okay. So V naught.
Excuse me. So can we see the sessions? Will it be available online later
Yeah,
for
sure,
review?
sure. It will be available. I have shared YouTube link, YouTube channel link. So where I'll be uploading. And one thing I'll try to upload on the day itself. So I'll try to upload by today itself. Let us see.
Oh, we
I'll
can
try my
see it
best.
in YouTube link. Is it so?
Yes, YouTube channel. Yeah. So
So the
save
link
those
will be
links.
sent to us, link will be sent to our mail ID or in the
I,
NPTEL
I
website,
have
sir.
sent in the chat
Okay, sir.
already.
Okay, sir.
You just check that
Okay.
link. And then one
Okay.
Excel sheet will be circulated where the link will be also presented. So you can
Okay.
access
Okay.
from there.
Thank you. Thank you, sir.
Yeah. So V naught is nothing but minus D by 1 minus D into V in. So if I substitute the values, I'll get minus 15 is equals to minus D by 1 minus D into 10 volt. So if I cancel minus minus and 5 3 times, 5 2 times, I'll get 3 minus 3D is equals to 2D. So 3 is equals to 5D. So D is equals to 0.6. So for the given condition, duty ratio is 0.6. Are you able to get it?
Yes, sir. Yes, sir.
Yeah. So now I have asked what is the range of duty ratio for the given condition. So what I would do is now I have to find everything in duty ratio. So my mod V naught is D by 1 minus D into V in. This should be less than V in. So if I cancel V in, then I'll get D is less than 1 minus D, or I can get 2D is less than 1. So D is less than 0.5. And naturally D is positive. So the range will be 0 less than D less than 0.5. Similarly, the other condition is greater than, so we'll get 0.5 less than D less than 1, the other region. So in this way, if you consider the magnitude, if we are trying to step up, then V naught should be greater than V in, then duty ratio should be greater than 0.5. Similarly, if you are stepping down magnitude wise, then V naught will be less than V in mod V naught, then duty ratio should be less than 0.5. So accordingly, we can choose the duty ratio. So in buck boost, we will be able to do both the step up as well as step down operation, and that's why the name buck boost.
Yes.
So everyone able to understand this problem and solve this problem?
Yes, sir.
Okay. Can we move to next question? Any queries? If you have any queries, you can ask. Okay. So next question is a bit different compared to this. Here it's a switched capacitor circuit. So there are two capacitors, 2 microfarad as well as 5 microfarad. And in the first problem, the switch S is on and then S bar is off. So the resistor is totally disconnected. Find the steady state capacitor values. And in the second problem, the switch S is turned off and S bar is turned on. Find the current through the resistor as a function of time. So in the first case, S is on and then it was made to reach the steady state. Once it reaches the steady state, then we have turned off the switch S, which means capacitor is connected in series with the resistor or parallel since they are two. And then we are asking find the current through the resistor. So is the question clear?
The first question you are saying.
Yeah, first part. So basically, let me draw the circuit. So only two capacitors are connected with the 10 volt and then 2 ohm is disconnected because S bar is off. So 2 ohm and 5 ohm are connected with to 10 volt. Two ohm and 5 ohm. So we have something like this. So this is 2 microfarad. This is 5 microfarad. This is plus minus V in. This is plus minus V2 and then this is 10 volt. So if you apply KVL, you will get that V1 plus V2 is 10 volt. V1 plus V2 is 10 volt. And then once it reaches steady state, charge on both the capacitors should be same. So once the charge is same, then only it means it has reached the steady state. So we will get C1 V1 is equals to C2 V2. So if you calculate V2, it will be C1 by C2 into V1, which means 2V1 by 5. So now if we substitute this back in the first equation, then we can solve for V1 and V2. So my V1 plus 2V1 by 5 is equals to 10 volt. So if I skip the math, it will be 50 by 7 volt. V1 is 50 by 7 and V2 is 100 by 5, 20 volt by 7. Is this fine? Once it reaches steady state, charge should be equal, which means Q1 should be equal to Q2. And I'll get one condition from there, and from the Kirchhoff voltage law, I'll get another condition. So my V1 is 50 by 7 and my V2 is 20 by 7. Okay, or let me re-explain. So in the first problem, S is on, so S bar is off. So 2 ohm is not at all connected to the circuit. So now this is the switching configuration, and the question was asked that it has reached steady state and find the steady state capacitor voltage values. So it should be find the steady state capacitor voltage values, not capacitor values. So at steady state, the charge should be equal. Then only it reaches steady state, else there will be still charge distribution. So charge will be equal means Q1 equal to Q2, which means C1 V1 equal to C2 V2, one equation, and one from the KVL, which is V1 plus V2 equal to 10 volt. So if you solve these two equations, you will get the steady state V1, V2 values. So is first part clear for everyone?
Yes, sir. We'll move
Okay.
to the second.
Yes. So in the second part, now what we have done, we have turned off S. So 2 ohm and 10 volt is disconnected and then S bar is turned on. So the resistor will come parallel to the capacitor 5 microfarad. So let us see. We have 5 microfarad connected in resistor which is parallel. And what is the value of resistance? 2 ohm. This is 5 microfarad. So this is 5 microfarad. This is 2 ohm. And this is what they're asking, IR of T. And say this is my IC of T. I am considering current capacitor, current is entering, and say this is my VC of T. So they're asking IR of T as a function of time. So I'll write the equations that I know for capacitor as well as resistor, and then I'll try to solve. So I know that IC of T is equals to C into dVC of T by dt. So this is one equation I know. And one thing I know that IC of T is nothing but minus IR of t. And then current through the resistor, how can I find? Say this is also VC of t, right? Both has the same voltage. So now minus IR of t is nothing but minus VC of t by 2 ohms. So I get one equation here, another equation here. So one I am getting from the capacitor and the other one I am getting from the resistor, because the capacitor voltage and resistor voltage is same. Current through the resistor is capacitor voltage by 2 because it is 2 ohm. So now if I substitute here, then I will get minus VC by 2 is equals to capacitance say C dVC by dt. So now I'll bring everything one side and then take the other things on the other side. So I'll get dVC by VC is equals to minus 1 by 2C into dt. So far is it clear?
Yes.
So now I'll put integral. I'll start from 0 to time period t. So Vc of 0 to Vc of t. If you see, capacitor has an initial voltage which is V2 20 by 7. So there is an initial because it is charging with a non-zero value. So my Vc of 0 is 20 by 7 volt. Okay. So if you solve this, you will get ln of Vc of t by Vc of 0 is equals to minus t by 2c. So if I do exponential and then solve, I'll get Vc of t is nothing but Vc of 0 into e to the power minus t by 2c. I have just skipped the math, but it is clear, right, how I am applying the integral and how I am solving.
Yes, yes.
So from this now I know that IR of t is nothing but Vc of t by 2 ohms. So if I do that, Vc of 0 is 20 by 7. So IR of t is 10 by 7 because by 2, 10 by 7 e to the power minus t by capacitance is 5 micro. So t by 10 micro. So in this way I can solve for the resistor as a function of time. So as t tends to infinity, current will be zero because resistor will fully discharge the voltage. So capacitor voltage will be fully discharged, which means VC will be going to zero as well as current will be going to zero. So if someone asks what will be the current at t equals to 2 microsecond, you have to substitute t equal to 2 micro and solve. But in this question, it is asked as a function of time. So let me just re-explain this question. So in this question, first of all, the two capacitors are connected in series, which is connected in series with the input power supply, and we were asked what are the steady state voltages. So using the charge balance, we have obtained the V1 as well as V2. Now they have changed the switching configuration. They have turned on S bar and then 2 ohm is connected in parallel with the 5 microfarad. But 5 microfarad is already pre-charged. So I have written the expressions for the voltages as well as currents, and I have tried to get one single equation with two unknowns. So then I have applied integrals, and you have to be careful that Vc of 0 is not 0. Vc of 0 is a finite value. So once we started with that, I have obtained Vc of t as a function of time. In the question, they have asked current through the resistor as a function of time. So I have converted Vc of t into IR of t using this equation. So is this question clear?
Yes.
Yeah. So to quickly summarize today's session, we have started with the buck converter equation for mainly DC-DC converters. We have seen the input output voltage relation for buck converter, boost converter, as well as buck boost converter. Then we have solved few problems starting with the resistive divider. We have solved output voltage, current, as well as efficiency. Then we have solved one problem on buck converter inductor current design, and we have seen what are the consequences of selecting a smaller inductor as well as a larger inductor. And we have seen where we should choose the inductor at what input voltage condition. Similarly, we have done the same for boost converter, and we have seen what is the worst case for the what is the worst case such that the inductor current will be ripple will be maximum, and we found the duty ratio is 0.5. And we have solved another such problem for buck boost converter. Same way we can do what is the worst case for this. that will be a little bit complicated, so we'll solve it in next week. Then in the last problem, we have considered one switched capacitor circuit, and we have seen how we can find the currents as well as voltages as a function of time. So that's all for today's session, and I think we are also past 7. So if you have any questions, you can ask, else we can end this session here.
Yeah, it's really nice. Thank you.
Thank you.
Teja.
Thank you. Yeah. Thank you.
Yes, sir. It's very nice. Thanks a lot, sir.
Thank you. And thank you for being so interactive. And this is what makes the sessions interesting and interacting. So the more you interact, the more it will be interesting for the audience as well as motivating for me also.
Thank you.
Okay, then see you next week, and I wish you all the best for assignment 1. Do well. Again, we'll meet next Monday, 6 o'clock with week 2 content. Good night, everyone.
Okay.
I'll try to upload the video by tonight, if not by tomorrow first off.
Okay.
Okay, then. Good night. Bye.